So we're going to present a system that is in development that has a very, very early prototype. It grew out of some of the work I did with data collection for video coming off the Predator unmanned aircraft, very high resolution cameras at 96 frames per second. How would you collect all of that? How would you analyze that? It comes out of some work. One of my colleagues here, Kevin Kelly's here from Rescale. He did a company with a friend of ours called Data Ingest, some ideas that came out of a company called Argyle. We hold intellectual property to this, but I'm here to try to continue the legacy of explaining where this very narrow part of HPC will become very important. Now, as preparation for this, I had some remarks, but I was driving here from my home in San Diego through the rain, but one part of my mind is focused on what am I going to say here, and I happened to pass an orchard. And the orchard, of course, no foliage, it's winter. The orchard was somewhat remarkable because the trees were all arrayed in a perfect grid, like the grids that we see here. They were just all very nicely arrayed, and it went on for a long time. I don't know how many trees, I couldn't count, I was driving, but I began to think, how could I use this idea of an orchard in preparing a talk, and why would it be important to data ingestion? And it occurred to me that this is sort of a definition of big data in one of my talks that I do, which is at the root of it all, which is the question you ask about your data defines the data, what part of the data, how you're going to use the data. The question at the beginning is going to define that. This comes out of our relationship at GA with CERN, because as you heard earlier, they asked the question, can we find the big particle? And all their data went away except the part that they needed to find the particle, and they found it. So the question I'd ask is, I'm a farmer, I want to optimize my harvest, I want to get the harvest to market and make the biggest profit. I need to find all the almonds that are ripe, sorry, all the pecans that are ripe at any given time on my pecan trees. So how would I figure a system to know where on, say, 1,024 trees, where are all the ripe pecans at any given day? Now, there's some interesting sidelights to this, because, of course, a tree has a nice shape, and in computer science we use trees, but every tree in nature is different, and the pecans are not just going to be on different places in each tree. Each year they're going to be on different places. So in thinking about this, of course, the first thing I thought is, well, what kind of result would I want? Well, I'd certainly want a visualized result. And in fact, want a visualized result where I had the orchard in a grid that I could rotate. I would have a measurement on that grid so that I could locate the pecans. I would want to be able to turn off the trees and just have the pecans. They'd be like dots in the three-dimensional grid. And the ones that were ripe would be green, and the ones that weren't would be red. How am I going to get to this place? Well, my background's in simulation, computational fluid dynamics, mechanical simulations. I've been building high-performance computing kinds, of which this is a kind of model, for a long time. So my first thought is, well, there's two ways to approach this problem of where are the pecans. One of them is simulation. Okay, I'll start with a seed. I'll have to know the entire rules of how a seed turns into a tree and generates pecans, which I'll identify as the Lagrangian of the pecan tree, of its growth. I'll have to know all the air conditions. I'll have to know all the soil conditions. I'll have to know all the sunlight conditions. I'll have to know when one tree's growing, the other tree's affected by it. Anything I do to one tree, affected by another. Now, I see there's two problems with this. The problem is there's not enough science to know how a tree grows. We simply can't simulate it. We don't even know where the tree branches. The place where it decides to branch, of course, we don't really know. The second problem is that even if we did this, even if, say, grew a tree in simulation, we'd still want to compare it to the actual tree, at least in enough instances that we could verify the data. This is something that comes out of my experience with computational fluid dynamics. They simulate a plane but they better verify it in the wind tunnel. It's still not enough to not verify it. Maybe one day will be, but. So you don't just do this for one tree, you do this for 1,024 trees. So I come up, well, how would I get the data from the tree in a very efficient way? And the first thing is, of course, we could have an individual climb up the tree with a plumb bob and measure where the pecans are, and then write it down and make a drawing of it. And so, well, that's kind of expensive labor-wise. So we might want to add sensors to the tree, but if we put sensors on the tree, it's going to affect how the tree grows. We're not going to necessarily know. That's not good for the tree. So I came up with this idea. I'm going to take a drone, and I'm going to fly the drone in a helical around the tree, and my cameras will be adjustable in focus. So I'll go up the tree at one focal plane, and I'll get pictures of all the tree, the tree foliage, all that. And then I'll bring them down, I'll go up again in another, and I'll have these cylinders, and from that three-dimensional data, I hope to run an algorithm that will create enough mappings that I can get the positions of the pecans. But now if you think about it, the resolution we're going to have to deal with for this grid of the visualization is going to have to be expandable enough that we get the whole orchard, and also detailed enough that we get each individual pecan, because to determine if it's ripe, we'll have to know the color, the texture, and all of that. I hope you can understand that if I can get this data from even one of these flights through all day long, by the time I get to 1,024 of these, I've got somewhat of a bigger data problem. First part of this is that if I only have one of these and I move it from tree to tree, by the time I get to maybe even the fifth tree, the first tree has grown more. There's more data, which I haven't captured, so I have to bring it back. By the time I did this, it'd be ridiculous to use only one of these. So this is a thought experiment. You know, these drones are absolutely free to my thought experiments. So I'll just have 1,024 of them. I can't create data by wires connected anywhere because the wires will get tangled in the tree. So maybe Wi-Fi or RF happens. Well, you know, from your cell phone usage, RF is not a very high performance network protocol, but it's enough to get to the base of the tree. So at the base of the tree, I'll put a data collection center, maybe NVMe, and while my things are flying up and down on all the trees, I'm collecting all this data. What does that resemble to me as an HPC guy? Well, it begins to look like I've got a bunch of data collection nodes that are going to run some algorithm that's going to actually take the data and reduce it to a point on that particular tree, and I'm going to have to collect all that data back, and I'm going to have to put it in my analysis machine that's going to create the positions of those and then visualize them. So let's start again with the visualization. We know how HPC works in simulation. We have some mechanism, which are these at the top of these in our head node, that represents our model. Say in the case of the orchard, it's just a model of the grid and maybe a stick figure of the tree that we're going to modify once we know the actual outline of where the pecans are. But to simulate this, all the data that we would use, the air temperatures, the wind, the seed, the growth, the scientific equation, they're in that. And what do? We take that tree and we put it on one node. We take another one, put it on the other. We break it up. We discretize the data. We have as many of these nodes of computation as we need, and then they do the work of simulating the tree, and they pass it back, and we make the big orchard. This represents that process. We're spinning this data, we're discretizing it onto the nodes. We're going to run our application on these nodes. They're going to simulate the growth of the tree, and we're going to eventually bring this data back, and we're going to have our simulation of the tree. Well, we kind of already know that this works, or doesn't work, because we don't really have the physics to do it. But on the other hand, well, let me explain what this slide is about. I've been working, this is an aside, I've been working in industry for a long time. I'm the biggest advocate of open source software. Visualization tools out there like ParaView and so on, they're great. Compilers are great. Flow modelers like are great. But I've also run a number of software developments in my lifetime, and I know that the biggest cost of making a system like the one we're proposing is going to be the cost of software development, the cost of the labor to do that. And to get all the open source tools in the world integrated, a year and a half ago I did an integration for a company of TensorFlow on GPUs, and it was a lot of fun. I had Skippy, I had Jupyter, I had all those. I did other things in that time, but over a couple weeks I got this all working. But there's a lot to figure out. And when I got done, I had what? I had something that one license of MATLAB would do for me for about $1,800 a year. Now, my experience with MATLAB goes way back. They have a distributed solver that runs GPUs on all their nodes. So if I want to do the simulation of my pecan orchard, I can get all that data down to a GPU, and it will do the solution for me. Now, interestingly enough, the way that MATWorks licenses, doesn't matter how many GPUs you have on that node, you pay for one worker license. So with NVLink, you can get these 16 GPUs from a company like Microwave, and you could do that very fast. So this kind of stands in for all the software you would do in a simulation. The other thing we like about this is, remember, the end result is a visualization that I can measure, that I can get data from, that I can create graphs from, that I can make a dashboard from. I like dashboards, but dashboards are just a shallow representation of three-dimensional or even four-dimensional in time reality. So let's do the four-dimensional reality and then derive the dashboard from it. But MATLAB has great visualization tools. Now, this kind of represents how MATLAB would work. We do these matrix multiplications. They represent our systems of linearized partial differential equations in our simulation. And again, we'd be running the licenses on them, but the end result is all of those aggregated in a solution on the head node. Well, let's think about this second model. We have all these data collection nodes at the base of all of our trees that are getting all that data down. What do they resemble? Well, they're our compute nodes. But this time our compute nodes are on the top, and they're actually data collection nodes. We're going to take the compute node, and even perhaps using the same one, by repurposing it, we can bring data down into the head node. And then what do we do? Well, we started with, in simulation, we started with a shallow model. Now we're going to take the data, we're going to aggregate it and get it into a model that can be visualized the way we need. Now, it's very clear if you think about it. We're not just talking about pecans on 1,024 trees, because there's an orchard elsewhere in the world. We might think about the orchard of pecan trees covering the entire Santa Clara Valley. That's not so far-fetched, because it was just decades ago that that's what the Santa Clara Valley did. They grew trees. It's one of the richest agricultural land in California in the West, and it's covered with silica now. That's fine. Silicon's worth a lot more than pecans. But how do we get from a big problem of 1,024, how many pecans are there in a tree in one crop? A couple hundred? That's just one crop. How do we get to cover all the state of California of this? If we're going to write a solution, and remember, writing the algorithm is the biggest cost, let's write it in a way that we can get to exascale faster and easier at the outset. Well, to me, what that means is that we want to kind of bit slice our data ingestion. We want to say, okay, we'll make data ingestion at this orchard as efficient as possible. Maybe we don't have one Ethernet connection to the grid for each of these nodes. Maybe we lump these trees in sections of, say, 25 each, and we have data collection from 25 trees coming in. We're going to have to link the nodes but we can link the data ingestion part from these things into a network interface card, and we could use another network interface card to link that to the other nodes. Now, why do we want to do that? Because you can and you want to. Because you might take the data that you're having on one tree and move it to your analysis node somewhere else. So to optimize this, this represents the Internet of Things at the top, which is our pecan trees. And these are our nodes, and we're going to put them in. And so this kind of just explains what I just was trying to say. Now here's the components of our solution. We have cores. The more the better. We have threads on those cores, usually 2 per core. Security's off there. It shouldn't be ignored. What are we going to do with this pecan data? Well, eventually we're going to store it. But before we store it, we might want to decide if we need it. We might want to analyze it. We might want to do all kinds of things with it. So we have the idea of we're going to need, of course, RAM, because we're going to need to create buffers to keep this data in temporarily. We might have, well, the switches, the routers, the compute nodes, the networks are all there. We're kind of calling this a virtual machine, but what we're really trying to say is this is like a hypervisor. This is sort of between what VMware would call hypervisor, but we're trying to be closer to the metal. We certainly think that running virtual machines on the cores would be one way we could do this quite easily, but in presenting this to certain people in academia, they told us, oh, you don't want to run a virtual machine. You're carrying too much. You don't really need it. You just need. So the idea here is we're going to use cores to. Now let's move on. We're going to use cores to control the buffers in our network information. So we're going to interrupt, and the interrupt is going to take the data that is collected from these NICs, and it's going to move it to kernel space, where we then can deblock the multiplex. So what do I mean by that? Well, the hardware that's available today, you have motherboards that have 16 PCI Express 3.0 slots running at 16 times. What we believe the proper network connections for data ingest should be is Infiniband from Mellanox. Mellanox, by the way, makes a 400 gigabit per second Ethernet card that's really slick. I don't even think you can operate a network at 400 gigabit to get enough data in there. Remember that most data from the Internet of Things is probably reporting from the devices at maybe no more than a kilobit per second. So I'd have millions of devices reporting into one Ethernet. Our friend at ARM, who was here last year, Brent Gorda, talked to me about, I asked him, well, how many connections do you think there will be in the Internet of Things? And he says, at ARM, we're predicting 1 trillion. 1 trillion by this year. So my idea is let's take the Mellanox cards, and as many of them as we can put out on our hardware, then what we need to do is one of two things. Either let's route Ethernet to the Infiniband protocol using some of their routers, or an older idea Mellanox had many years ago in their 56 kilobit per second ConnectX card was, let's tunnel Ethernet through Infiniband. And where is it shown? Oh, it's shown down here. So the idea is that in a 200 gigabit per second Infiniband card with Ethernet tunneling, I could bring somewhat less than 200 1 gigabit Ethernet streams into that, and then at the end, I would have less than 200 somewhat IP address sockets that would unload these streams of Ethernet. Now, each one, because of this problem that there's the disjointedness of the number of bytes reporting and the capacity of the fabric, you still want to demultiplex them. But with Ethernet tunneling, if it were available from Connect, and it isn't right now from the ConnectX 200 gigabit, if I understand Mellanox correctly, it isn't. But if it were, then I would have for each one of these connectors 200 IP addresses. So let's say I had 4 of these for my data ingest, and then I have 1 of these to connect to the other compute node. Now, why do I want to do that? Because once I've got the data in my user buffers, I'm going to use the cores of say, Skylake or of an NVIDIA GPU. I mean, we're proposing that with an NVIDIA GPU, if we could get enough cores that through their host unified memory, we could get the driver to understand from the NVIDIA device how to watch the buffers, then we would use the features of the cores on the card to control the buffers and control the data size and move it for us. So threads do 2 things. They control the data ingest from the network interface into the buffers from user space, and they also do one other thing. They message pass. One of the differences that we want to do besides maybe what other people are doing is for every interrupt, we want to pass a message telling every other, well, telling the head node, telling every other ingest node what each of them are doing. Then I can load balance. So with 2 threads per core, I can have 1 thread watching 1 ingest buffer in kernel space, and when it's filling, it's moved to user space. I can have the other one sending a message to the head node or any other core saying, this is what we're doing, be aware. There is a MPI implementation for NVIDIA, for the NVIDIA GPUs, so it's possible to message pass inside them. We liked Knight's Landing because of a lot of cores, a lot of threads, but it's gone. But Skylake is getting there, right? 48 cores, I think, next year. Down here below is another illustrative idea. Last year, a guy was here talking about microservices. Well, one of the microservices we want to do is we're ingesting different data from different formats. How do we know when the data coming in matches a format? Well, we would have a little pipeline where we'll load formats that we know are expected in RAM, and we'll just compare in a decision tree the packets coming in with those, and then we'll keep all of this information in an in-core RDBMS, a relational database. That way, when you boot the system, again, MPI will go out and run a setup. We know all the hardware. We know what the formats are expected to be. Another service that we're imagining, though, is, okay, let's go back here and did the wrong thing. What if you don't know what the data is? What if the data is a complete mystery? Can you discover a pattern in the data and decide on that basis what to do? That seems to be a very good rationale for machine learning. There's already a system out in the world that kind of does that. It's called SETI, the Search for Extraterrestrial Intelligence. They're looking for patterns in data. You have 3 cases right off the bat. All the data is 0, all the data is 1, or it's completely random or pseudo-random. That might not be of any interest to ignore it, but we're thinking along those lines. Now, another feature of this that came out of the work I was telling you about with the video is another reason to use MPI and RDMA is with MPI 2 and now with MPI 3 and the advanced the whole memory of your nodes, all of your compute nodes, is going to look like one address space to MPI. So if we were bringing something in on, say, 200 interfaces, bringing in streams of video, and we want to, switch the frames, like reverse the film or mix them or just process them in different ways, we want to be moving those buffers in core, because if we have to store it and have to get it back out of storage, the I/O is huge for that. So the last part of this, which I'll get off the podium in a minute, I'm a member of a group of advisors to a project out of North Carolina, Chapel Hill, called iRods. iRods is the back end to what we're doing. iRods has a kind of data ingestion system based on Python right now. iRods stands for Interactive Rules-Oriented Data Management System. And what it does is very simple technically. It doesn't matter where your data is. It doesn't matter what format it is. If you've got data in a buffer, like we would when we're ingesting our data in RAM, if you have data in an RDBMS format from any vendor or Postgres, if you have data in a flat file, if you have data in ISAM, VSAM, whatever, to your application, iRods will present a flat POSIX file system. So you can actually do this with iRods. It's kind of cool. I have a relational database in core on 128 compute nodes, but they're independent. I want to create a view for processing of the entire 128 as if it's one data view. With iRods, I can do this. I can get this view, I can put my data into the view, and iRods automatically updates those RDBMSs in the right place, the right way. The consortium of this has been growing. This originated at the San Diego Supercomputer Center. At General Atomics, we had a version of this, which I got started, and then they have decided to pull the plug. But Bayer, the pharmaceutical company, is a part of this. The European Data Collective is a part of this. It's open source. You join the consortium if you want help. But I would have you guys look into this, because no matter what you're doing with data, if you want it moved all around the world transparently, iRods is the way to go. So thank you very much. Are there any questions? Oh, yes.
Just a comment. There's a very successful business case for drone vision on the surface. What they using drone is to inspect the field that counting how many produce that
Yes.
is about harvest.
Yes.
And then the farmer and produce dealer can agree on a price.
Yes.
And also the government get early warning that if the weather is good, and
Right.
the produce gonna oversupply and the price gonna collapse. So they can preemptively arrange the cold storage or export. And so we'll be able to be able to keep the price stable.
It's like microsecond trading in commodities for pecans, right? We'll optimize the pecan market. This is something, at General Atomics, I participated in the design of our Predator unmanned aviation vehicle. And people in the news hear about it, it shoots terrorists and everything like that. Well, actually, the fires up here, it flew into the fires closer than any manned plane could go to spot the dumping of the water, They're really neat things they can do. One of them is look at fields from the air with, even a mass spectrometer, figure out how healthy the plants are.
It's a third party as a service between the farmers and the producers.
Well, we'll talk to you about that, because just another little plug for Integral Engineering before I go. So Integral Engineering is a very small company. We hire associates. Most of our associates are retired people my age or older who have years of service in, guess what, HPC. I mean, I have an associate that is retired who has been working with MPI every day, with OpenMP every day for 25 years. We have people versed in the simulation analytical tools. Been doing it. One of my friends is 80 years old. He's the only guy that knows the APDL language in ANSYS. So my pitch to you guys is this. There is ageism in our industry. And I have heard people half my age say, not directly to my face, well, you guys have good ideas, but you're dinosaurs. So I'm here to say, I am a dinosaur. We are dinosaurs. Wait a minute. We're the dinosaurs as they are portrayed in the movie Jurassic Park. You let us off the island, you hire us. we will eat your competition alive, okay? And thank you.